Well, welcome to our February additional structural modeling video conference. Today, Kevin will be discussing relationships. I believe it's the influence relationship. And I'll be turning it over to Kevin. If Kevin's there, let's see. We have Kevin's mic is off, so it might be a little bit of a, can't hear him either. So we'll just kind of wait a minute here and see if Kevin is available to work the presentation. These additional meetings are kind of unstructured, and we kind of go through and pick a subject that everyone is interested in. This one right now is on the influence relationship. Kevin was going to continue his discussion of this area, and which is a little bit different than some of the other types of structural modeling relationships that we've been talking about. And probably in the future, we will look at these in a little more detail and bring together a situation where we have a little more a little more well-defined characteristics on the differences between the relationships, so we can talk about their impact on structure and so forth. So,
yeah, I think that's really important. That's really important, Joe. I was just thinking exactly that. I mean, who has made the definition of what influence means? For example, did Warfield actually identify influence as a particular, what would you call it, category or description of structure? Or is Kevin going to cover that?
Yeah, I'm not sure what Kevin's going to cover. As I said, these are a little bit unstructured, but one of the things that I noticed when I was reading through the history and background and looking for different types of relationships that were documented in the literature, I noticed, I also read Warfield's autobiography, and I believe the influence, not influence, but the exacerbates or aggravates, right? The aggravates relationship, Warfield said was basically pioneered by Christakis, I believe. So there's certain people that have used certain relationships. So Kevin, are you there? Let's see, maybe I'll check the chat, see what's going on here.
Yes, can you hear me?
Oh yeah, there you are. I can hear you now.
I was trying to connect by computer, but it's not doing it.
Aha. Okay.
But so I'm on the phone, but I can start anyway.
All right. Would you like me to? Okay. Well, however you'd like to do it.
I have an outline that to follow to talk about this relationship. And first, remember that the reason we're doing this is because there are languages used today that have over the last half century, conventional languages have emerged, and starting with the movement in object-oriented modeling and analysis back in the late 80s, early 90s, they've kind of evolved to unified modeling language and then systems modeling languages standards. And those, I mean, there are many other languages that are used in software engineering, like Schler-Miller modeling and process modeling and these types of things. And so what I've I think it's important that we view our inquiry tools as being able to deliver languages that people use. And much of the Warfield and Christakis community back in the early days were proposing languages that no one came to use. For example, one of the first languages they proposed was called Grail, Grail. It was meant to be a graphics language that had logic built into it, and it never caught on. Then they had a language called Delta Charts, which was like a PERT chart, which was links between activities, but they added logic gates, like an electrical engineer might, and an OR gates on each side of the activity. So you could say if a certain number of activities were required to feed into another one, you could say if it was optional by using the OR gates and so forth. And they felt this was a great advance. It was better than PERT charts because it gave you more power, and no one ever came to use it. And next, one of the next ones that Warfield came to spend the rest of his world on was the Problematique. And we'll talk a bit about that. But when they were first starting, they outlined over 60 different relationships that could be modeled, natural language relationships that could be mapped to the mathematics underlying structural modeling. They did some of them, correct curriculum structures, which is basically a precedence relationship, priority structures, which is a total order, something called enhancement structures, which is actually a complement to aggravation. But we have to remember that what we're modeling a structure has a node and a link, and the nodes should be all of the same type, and the links are all of the same type for one modeling run for how all of the software works that does structural modeling. However, the languages that have emerged typically have 3 relationships amongst the same items. So in object-oriented modeling and its version in unified modeling language, you have aggregation relationships, which are part-whole relationships. We had a discussion about that. I did a presentation called Mereology, which is about the logic of part-whole relationships. They have classification hierarchies or type of relationships. These are associated with class libraries in software modeling. And then there's functional relationships. In object-oriented modeling, they would be called methods. That's when one thing is a function of another. And the most persistent type of relationship that's been modeled in structural modeling related to that is the influence relationship. It's a little different than a function, and so we can have some discussion about that. So that's just as a background. The reason I'm going through this is to help our community take our heads out of our methodological sand and look what the world's doing. The world has languages that it speaks, and we should be able to help them produce more robust and larger models. So most of the modeling tools that like the software engineering world has for doing the models, doing the object-oriented models, is you have someone interact with things by pointing and clicking. They connect two objects and have a relationship, and they connect another two objects, but they don't have a mathematics behind it that's ensuring that there's a propagative relationship there. It's just, it accepts what the user does. And so we have a tool that can be really helpful in people understanding long-range propagation of relationships that most of the current software tools for unified modeling language and object-oriented modeling don't do. So we have a nice tool to introduce to them, but we have to say we're ready to speak their language. And if we go to them and say, yeah, we model problematiques, they say, thank you very much. We don't care. What the hell is a problematique? We're trying to do object models or process models. So so let's talk about, we talked about the part-whole relationships before. We also talked about the type of or kind of class hierarchy type of relationships before. Now we'll talk about the influence relationship. And those three types of relationships are what's needed for most modern day modeling languages. And so in contrast to all the work that Warfield and Christakis did, they never did models that have more than one relationship on the same objects. That's an important thing to note. And that's where our community stands. If we're going to step into the world, the real world to help people that are doing modeling in the currently accepted languages, we have to step up our game compared to what Warfield and Christakis were doing. Now, so let's talk about influence. The influence, when I first got interested in the influence relationship, is because I was doing IDEF modeling. IDEF was for the ICAM definition language, which was integrated computer-aided manufacturing definition language. It was an Army project or an Air Force project back in the 70s. And you did functional modeling. And they had IDEF 0 was functional models, and IDEF 1X was entity relationship models. And then they eventually developed, I think, over a dozen different IDEF modeling formalisms. But I was doing very large models that had 5,000 to 6,000 functions in them. And so we had a massive difficulty considering anything but local relationships. And that was why I got intrigued with the use of interpretive structural modeling. It's a potential way to break through that. And so what's the relationship of influence models and functions? Functions by definition are transitive relationships. And they're typically asymmetric. So, the mathematical function fits what interpretive structural modeling pre-Simpson was doing, just that combination of relationships and excluding recursive functions, which would get us into reflexive relationships we don't want to talk about. But the function, the basic mathematical function, I think is well modeled by the structural modeling formalism we have. Now, to bring it into modeling something like IDEF, you need something that's a little more, has a little more richness than a mathematical function. So one of them defined by his name escapes me at the moment. He was a big guy in operations research. And he defined what he called the producer-consumer function. That is, when you have functional relationships, you can view the first item as the producer and the second item as the consumer. And behind that relationship there's probably an object that you could identify that's being consumed or produced or consumed. So that's a little richer than just the idea of a function. It's a dependency, and it's a dependency that has an object behind it. And so when you're doing modeling of things like processes or production models or software programs, it's a way of thinking about what you're doing. You can ask, does something produce something that the next thing consumes? And that's a richer way of asking a question than just saying, is A a function of B? You can say, is A producing something B needs? And that's a little richer use of language around the idea of influence than just a function. Now, a function, influence is a bit fuzzier than the notion of a function. We have the idea that if C is a function of B, that if B changes, C changes. But if we say, is C influenced by B, it's not clear that if B changes, C changes. It might change. It depends on the additional constraints in language that you build on that relationship. For example, when you're asking, if you're doing structural modeling and you ask, does A influence B? Let's say yes. Does B influence C? Let's say yes. Are we asking, is it necessary? Is it a necessary relationship? Does A necessarily influence B? Or is it just asking, might it influence B? A few days ago, Joe was having a discussion with Len Troncal, I saw, where they were asking about the notion of, was it partial causality or partial influence? Was that it, Joe?
Yeah, that was it.
Yeah, and so this is related to that. Is it when you do a model that says A influence B, and you don't have anything else there, it doesn't necessarily mean there isn't anything else. It just may mean that you haven't inquired about it yet. And so you don't want to say that A is sufficient as an influence of B, meaning there may be other things. And so whether something is a necessary relationship, does B necessarily need A? If A happens, do we know for sure that it influences, or does it only sometimes influence? So there's also modal operators. For example, a three-value relationship could be no, there's no relationship. Yes, there's always a relationship, or maybe there's sometimes a relationship. A four-value modal operator could be no relationship. Yes, there is a relationship. No, there's only sometimes a relationship, or there's always and only that relationship. So that would be a four-value relationship. Now, all the structural modeling tools that I've used are just two-value. The matrix that Joe is using, for example, is representing the relationships or lack of relationship by ones and zeros. But you can have modal operators that have a four-value logic. And instead of using Boolean algebra, you use four-value logic. There also may be levels of certainty involved with your relationship. For example, already by the early 1980s, there were fuzzy logic implementations of structural modeling happening where they had a range of potential values, not 0 or 1, but a range from 0 to 1, depending on how certain you were about the relationship. So this is the idea of a weighted relationship. Now, in Warfield's time, he recognized the potential use of weighted relationships, and the way he dealt with it is he would do the hard relationship, just everything is a 1 or a 0, and then graphically with a pen on the diagram list whether an arrow between two objects had some weight, whether it was a really strong relationship or a weaker relationship. So he would just represent it graphically. A practical way to do that is a way to come up with the weight is if you're using a group to decide, does A influence B, and 7 out of 10 say yes, then you can weight that arrow as 7 points on a 0 to 10 scale in terms of thickness, and just do it graphically. And I did a project like that where it was for the Food and Drug Administration, and we had enough information and enough people working on it that we weighted all of the arrows in the diagrams, and it was based on votes. So now let's talk about versions of an influence diagram. So you can cleave the meaning of influence in two. You can have a type of influence which is only bad influence, and you can have good influence, right? So bad influence is an aggravation relationship. So does A aggravate B? Does B aggravate C? We can infer A aggravates C. And so if when you're doing aggravation, we presume that the nodes are problems or challenges. So we presume that if A gets worse, problem A gets worse, and it aggravates problem B, then problem B gets worse. And you see in here implicitly is a signed meaning S-I-G-N-E-D, whether there is a plus or a minus at the end of the arrow. When we do a problematique, we assume it all by saying they're all the nodes are problems. So if a node increases, it's getting worse. And all the arrows aggravates imply that if A increases, it's going to increase B. But if you have an influence diagram and you wanted to represent that subtlety, you would say, does A influence B, yes or no? okay, does it influence it positively or negatively? And so you can add a sign, a plus or a minus at the arrow, and basically have both an aggravation type of relationship as well as an enhancement type of relationship. So, so you have to be careful. A lot of people, when they go to do influence diagramming, they don't think of the negative side that influence includes. They just treat it as an enhancement relationship. So enhancement is a type of enhancement structures were a type of thing that Warfield did quite a bit. And but he came to focus all his time on aggravation and problematiques. I'm not exactly sure why, except when he came to work with Ford, that was almost all they did for years, like 5 years, was problematiques. Joe, do you have any insight as to why he came to focus on that?
You know, really, Kevin, I don't. I think there's a number of things that might have that might have impacted that area, and I think one probably was the access and the development of the technology support at that time. They were using you know, with I guess it was Staley there at the Ford Research.
Yeah,
they were going through and did quite a number of extensive events. But I think the main thing there, and I think that there's two parts to what's going on with the total package of it, of an activity. One is the organized process by which you bring together an organization, a very large-scale organization, to address the situation. Then the other part is the technology and how the technology is used to aid in the exploration of the unknown or poorly defined problem. And I believe that was really a balance. Using a problematique and that kind of general concept is something that everyone in a large organization can understand. It doesn't take a lot of time and pre-preparation to bring people up to speed. And so I think that's part of it. But there's also other parts going on. So
yeah.
I'd like to comment, if I might, on that as well. That it struck me that framing it in a problematique, then the next question that seems to arise in the way that ISM and Warfield seems to have developed is, what are the barriers to something? And it's not framed within the context of perhaps design or a positive move.
Right. So there's a number of I think social and communication and organizational issues associated with picking the context and the specific structure of the triggering question. And it's interesting, and it's an area where I think the social scientists and the organizational folks could provide a lot of insight, you know, as we develop the technology a little differently, open source it, make sure people have access to it, understand it a little bit, let them play with it, see what they think. So yeah, there's a lot of things there that could be very interesting.
Exactly, and that's why I'm really grateful, Kevin, for your explanation thus far this morning. It's very helpful in that regard, because what came to mind as you were talking is and particularly as some things were developed and accepted and some were not, in terms of languages that Warfield invented, like Delta, for example. It would be interesting for me and maybe some others to apply the technologies that we're talking about, the structuring approaches that we're talking about, to the acceptance and implication and implementation and usefulness of structural modeling in different domains. I mean, systems engineering being one immediately, of course, of interest and concern and receptivity is, you know, how could we apply structural modeling to understanding the acceptance of structural modeling within systems engineering, for example, as it is currently described, or maybe even helping us to describe it better now that we have sort of Simpson et al. Developing all this great work.
Mm-hmm. No. So I'll mention another little set of modulations of working with the influence relationship. There's ways of applying calculus to this. When you're asking, does A influence B, you could ask instead, does making progress on A help you make progress on B? So that's like taking the derivative of a structure, a rate of change. You're changing the question into a rate of change question, and you can, so that would be like a velocity structure. And you can do an acceleration structure. You could ask, would progress on the change of A help you make progress on the rate of change of B? So that would be asking about acceleration. And that's the psychology of that is it's asking about a motive force. Is there good momentum in a group? Would momentum on something help momentum on something else? People have an intuition about momentum. And I think asking something like a momentum on A and momentum on B is more intuitive than asking, does A by itself change B? People have more of a dynamic sense, and we have a language about the idea of momentum, which is natural. Whereas asking, does A influence B, is almost a little more contrived than asking, you know, do we have enough momentum to affect something else? And then there's another twist, which is to change a problem critique into an action model by the way you ask the question. And this would be go for problem critiques, problems, barriers, challenges. So a typical one is, instead of asking, does challenge A aggravate challenge B, you could ask, would overcoming challenge A help you overcome challenge B? And that turns the problem critique into an action plan. That's not typically going to be as detailed as you want for an action plan, but by the use of the language by which you ask, you're basically asking about an action, about overcoming a challenge or overcoming a problem is an active question without asking us specifically about actions. So, for example, if we're working with a group and they only have one day to do the work or 1.5 days to do the work, we only have time to go through one structuring operation with them. So what do we do? If they do want to talk, if they do want to get into the space and talk about their problems, and they don't have time to develop an action plan, then instead of asking, does one problem aggravate another, we'd ask, if we overcome a problem, does it help you overcome another problem? Which gets you into the action domain. People speak in more of an active mindset, action-oriented mindset, rather than an analytic, descriptive mindset. The problem definition, understanding systems of problems, is largely a descriptive mode of thinking. It's not an abductive, hypothetical, action-oriented mode of thinking. And so, but what I'm just pointing out is, even if you're using the names of the nodes as problems, obstacles, barriers, challenges, you can get the active mindset by asking about overcoming them. So I think, let's see. Now I'll just mention, if you search for influence diagrams on the web, you will not get the type of influence diagrams that we're talking about. There is a branch of decision theory that does influence diagramming, and it's largely tied up with sophisticated use of statistics or Bayesian reasoning, and it's more mathematical than the influence diagrams that we're talking about. So don't get confused if you start doing searching. All the literature is not about what we're talking about. I think I covered all the various aspects of influence diagrams. I wanted to suggest that we go over. It just saw I can summarize that there's a structural relationship we model that's represented by ones and zeros in the matrix, or a directed acyclic graph or diagram, where the links are represented by ones and non-relationships are represented by the zeros. A first level mapping of if we want to go beyond a matrix or a graph to something more meaningful, as one step towards what we're talking about, is a function. A function, if B is a function of A, in engineering terms, when A changes, B is going to change. And we can do rates of change and things like that. We take derivatives of this. This is how engineering works. We can also take the derivatives of it by language. So if we say, what's the rate of, how does B change? How's the rate of B change as a function of the rate of A changing? We do that with calculus, but in structural modeling, you can do it with language. A step more sophisticated than talking about functions is producer-consumer functions, that you can presume that in pairs that have a relationship, that one thing is the producer and the second thing is the consumer. And it's often helpful when you're doing inquiry to say, can I identify an object that is being produced and consumed between those two functions? I'll note that in terms of the mathematics, if you have A influences B and B influences C, and those, or you're saying C is a function of B and B is a function of A, that those functions can also be, they can be on the nodes or on the arrows. And it's sometimes helpful to view them both ways. But a step up from producer-consumer functions is the idea of influence. And influence, when we ask something influence, it means, does it influence positively or negatively? It's a composite type of dependency. The dependency can be necessary or sufficient depending on how we constrain it in the use of the language around it. I'm not sure if there's implications for the math about doing things that are necessary or sufficient, but it's a constraint on how we can treat the inquiry. The relationship can have a partial cause, or we could say it's always and only that relationship, and there's no others. So that would be, whether it's a sufficient relationship or not. There's a way of dividing the influence to have a more focused, a narrower meaning, such as the aggravation relationship in problematiques or the enhancement model. We talked about the notion of signed graphs, whether there's a plus or a minus at the arrow. So if one thing goes up, does the next thing go up or down? That plus and minus is essential for using influence diagram type of modeling for doing systems dynamics. So if you want to use structural modeling to generate a systems dynamics model, then you're going to be using the signed graph. And as I mentioned in Warfield's day, and still the way we do it today, is you would model the general relationship. Is there influence at all? And then refine it by just manually putting a plus or minus into your systems dynamics software. We talked about changing problems into actions by asking if you overcome the problem, it puts you in an action mode. And we talked about the use of calculus. If you make progress on something, or if there's momentum on something, does it help progress on something else or something else's momentum? And also that there's weighting of the influence relationship, which may be based on certainty. It could come from voting. It could come from Bayesian estimates of uncertainty. And that's right now, I don't know of any structural modeling software that allows you to weight the relationships. It's something we do graphically and keep track of manually. So I think that's it.
Well, that's excellent, Kevin. Covered a lot of interesting areas. And I guess probably one of the, well, I'd like to take a few minutes now and just take what I perceive, what you've said, and put it in a little bit of context with what we've been doing with the structural modeling activity over a period of years. And some things we'll talk about in the next technical report. But one of the things we'll talk about is the art construct. And the art construct has numerous two-dimensional matrices that you can put together and perform functions over them. So one of the things that I found when I was looking at these mathematics where they just had a single matrix and were doing all these different types of symbolic augmentations, that the matrices themselves became very cluttered and hard to understand and to do computation on. So there's really no penalty from a computation standpoint just to have a whole series or 3 or 4 n-dimensional sets of these types of matrices where you perform work on those, and then you can aggregate them in any way you want. You can perform the functions over the matrices as opposed to performing or in addition to performing functions over the nodes. So we've published on that quite a bit about 10 or so years ago. And then the part about the language, the decision points in the language and the rule sets, about the time that Warfield was putting together in the early 70s, those concepts of decision making and rule sets is when Prolog was developed. So there's, in my mind, one of the real advantages of the type of inference that you can do using structural modeling is you can do inference without using a specialty type of rule-based language. Now, it's not universal. It depends upon the characteristics of the relationship that you're looking at. So, and that's another area that's quite interesting to me anyway. And they're talking about systems dynamics. We worked with the earlier on, we worked with the idea of large-scale matrices of objects that were related in some way, precedence, influence, whatever. But in that case, what we found is you really needed to start your initial conditions where you needed to know the object set that you started with, and then over the large scale, what you were looking for is you're looking for some type of optimum, either minimize resource construction, minimize, excuse me, some type of design criteria. And so we were using evolutionary programming, large-scale search in those cases, but also we could decompose those into different matrix sets. I think the next technical report is going to take a little bit more of a step away from the direct software, talk a little bit more about the connections to the abstract relation types, how that works, and then I'll start expanding some of these areas. But I think these are great ideas, and they're things that need to be developed, and that there's kind of the application, how do you actually introduce these to large organizations? And then the other part, of course, is how do you actually put them into software or into tools that will help large groups of people make decisions and be able to understand things that they're kind of overwhelmed with now. And I have a tendency to call this augmented intelligence, but as I said, again, we'll do a little bit more of that in the next technical report. So that's kind of what I had to say.
That's really interesting. Could you say a little bit more? I like the idea of augmented intelligence. Could you just say a little bit more about the relationship to evolutionary programming?
Oh, okay. Well, so if you have, so if you're searching for a specific combination or a specific configuration in a system that optimizes some parameters, and so you want to be able to look at those and come up with a configuration. So the idea about evolutionary programming is that you're always looking to improve against some optimized or some optimization rule. This is good, that is bad. So we want to move toward the good, and we want to move away from the bad. So evolutionary programming is a way to do extremely large-scale search for these combinations, and then look at a set of configurations that may or may not, they're all kind of close to optimal. So you take the machine, you have the machine do its work, and then you say, oh, okay, instead of, a million different permutations, I'm going to have the machine select the top 10 candidates here and then show those top 10 candidates to experts or individuals and then let the human beings make the decision or the pick among those 10 instead of, giving them the job of looking at many tens of millions of things, which is just impossible for people to do.
Okay, that's helpful. Thank you. And what about then, going back to what Kevin was saying about influence and Warfield using sort of 0 and 1, but then doing things graphically in terms of representing it, drawing it, I guess, with thickness of a band or an arrow representing the strength of the influence. And then the comment that there's no way to weight particular, what do you say, Kevin? There's no way that he knew within structural modeling to weight particular choices.
There is some weighting that goes on, and I think it was just a technology constraint. That period of time, the technologies they were working with didn't allow them to do these more sophisticated types of activities, but Go ahead.
Yeah, in the early 80s, when kind of the flurry of research on structural modeling started up in Japan. Fairly shortly, they had fuzzy logic implementations of structural modeling. So that is a weighting. They're able to do a weighting. What the weighting means, it depends on what your semantics are. The weighting could be uncertainty. That's what they were dealing with, was uncertainty. But it could be weighted strength. Yeah, so there's instead of using Boolean logic, which are around the ones and zeros, they were using fuzzy logic from Zadeh. Fuzzy logic was big in the control industry in Japan at that time, and everybody knew how to do it.
Has that dropped off now then? Is that not current, or is that where is what would you say is the current state of play in looking at these various things? Is it all rest with Simpsons, and where is this?
Where is what? This research?
Yeah, I mean, well, you said like fuzzy, different. Yes.
Well, it's hard to say because these practices and tools got internalized in big companies, and they didn't publish about them.
That's right, for competitive reasons. Right, exactly. Yeah.
Yeah, so for example, Northern Telecom did a big investment to write their own versions of the software, and there were some, like some conference presentations and very little written. But then the guy that was behind that or involved with it at Northern Telecom left and started his own consultancy. And then he had a lot of publicity about his own work. But he didn't publish how he did it or what he was doing very much. Almost no publications. He was just doing professional consulting with it. And, in Japan, it was in Fujitsu, Nippon, Hitachi, and the things that we have as publications from there were when their partners in the local universities, like Hokkaido University, had people doing structural modeling research, and they would publish about it. But most all of the publications they had were in Japanese. So I knew they were doing it because it would come up on literature searches, but I couldn't read it. And then it went. Then there was research in the Middle East. It got kind of inculcated into Saudi Arabia. There was researchers in Iran, and then there was a kind of a blossoming in China and Taiwan. and China and Taiwan still probably one of the most frequent publishers on structural modeling, but it's most all in Chinese. And India. India was probably before China and Taiwan in terms of the publication surge. Now, most of the stuff that they publish now is not research about structural modeling. It's research using structural modeling. And they're doing something a bit different than what we're doing with the software. Most of the publications I see coming out of India are using a manual method that is several steps shy of what we call structural modeling, and they're not using software that allows them to take advantage of a matrix math. And as a result, most of their applications are pretty small scale, like 10 ideas or 20 ideas at the most.
Okay.
And so, yeah, go ahead.
Well, I was going to say the other thing that I would be interested, apart from what you've said here today, is there any paper or anything that would put the influence diagramming and influence structuring in the way that you've presented it here today alongside or compared to the Bayesian approaches that you mentioned?
No, there isn't anything I know of, and I don't understand the Bayesian approach well enough to write one myself.
I just think it would be helpful to be able to describe the distinction between the difference in meaning when encountering someone who has more experience with influence diagramming and influence modeling, influence language in that area, as opposed to the structural modeling as we're discussing it.
Well, I would say that. Well, go ahead, Kevin.
Well, the influence modeling that we're doing is much closer to doing systems modeling and unified modeling language modeling and object-oriented modeling than the influence diagrams that are using statistics for statistical reasoning.
But one of the primary differences is with what I see is that that structural modeling starts with an unknown system or a poorly defined system. And Bayesian types of things, you need a prior probability. Bayesian, you need quite a bit of information initially. With the structural modeling, you don't need that information. You're going to develop that information. So it might be, as a matter of fact, that you would use the structural modeling a little bit and then develop the information you would need by using these influence techniques to then create a Bayesian model.
Exactly. That's very helpful. And I think the ordering of that structuring is very important to lay out. And we should diagram it in some way to be able to explain it and its appropriate and the appropriate selection of the particular kind of modeling, influence modeling or whatever, at a particular stage of any encounter or situation that is being addressed, whether it be or whatever it be. That would be very helpful because that doesn't really exist that I'm aware of. And what you just said is very helpful, Joe and Kevin.
So there's a lot of connections and a lot of ways that these things can be put together. But I believe a discriminating factor about structural modeling is it's designed to use when you have an unknown situation. And then you start working that up and creating information. Depending upon where you want to go with that information, depends upon the techniques and types of information and stages in the structural modeling activity. But Kevin's much more of an expert in that area than I am. But what we're going to try to do with the abstract relation type is be able to package and modularize this information steps, and so that we can do basically a little bit of what you're talking about. Say, okay, you develop it, you develop your information to this point, then you make a decision. Depending on what your goals and objectives are, then you might go one way. If you wanted to do a Bayesian model, if you just wanted to do a structured matrix discrete model, then you might go another way. So yeah, we're headed in that direction.
Excellent. Thank you very much for a good session today.
Anything else you'd like to add, Kevin?
No, I mean, what I went through today, I just jotted down a list because I didn't have access to the computer with previous presentations. But what I realized in coming up with the list is I don't know anywhere that this variety of aspects is written down in a very succinct way. That this is gleaned from across many of Warfield's papers and his books and things, and there's not a consolidated presentation of this anywhere.
Well, might be a good idea for you to maybe develop one and present it in about a month.
Yeah, might be good, especially as to how it relates to things in systems modeling, because we're trying to get us into being in the service of systems engineers rather than promoting our own lingo.
Yes, Rosetta Stone.
Huh?
All right then. Well, it looks like we have a topic for a month out, and we'll have our read ahead hopefully up on ResearchGate here in the next week. And thanks everybody for participating. Good session.
Thank you very much. Bye for now.
Take care, Gavin. Talk to you later.
All right.